So today we are going to revise the second chapter of M2 10th SSC Board Exams, Pythagoras Theorem. So this starts with a simple recall of what the Pythagoras Theorem is. So what the Pythagoras Theorem is simply that in a right angled triangle, so for any triangle that has one of its angles as 90 degree, which is a right angled triangle, in that triangle, the longest side, the hypotenuse, the side which is opposite to the right angle, to find the length of that side, we have a special formula, and that is that for if we take this triangle as an example, we can say that PR squared, that is the length of the longest side, this side over here, the square of that length is equal to RQ squared plus PQ squared. So this is the basic Pythagoras theorem. The length of the hypotenuse A squared is the length of the other two sides squared, the sum of the length of the other two sides squared. And why is that so? So the proof we are going to learn a little bit later in this chapter, but for now this is the basic Pythagoras theorem. This is just a formula that you have to remember for the exams. You can, after learning this proof, this formula will become much more easier to remember, but this is just a formula. This is how the triangles behave, the right angled triangles. After that comes the Pythagorean triplet. So Pythagorean triplet is nothing but any three numbers that follow this property. So which property? This property where the largest number, the square of the largest number, is the sum of the squares of the other two numbers. So let's take this as the example. So we have 11, 60 and 61. So which of them is the largest number? 61 is the largest number. So if this is a Pythagorean triplet, then 61 squared should be equal to the other two numbers squared, the sum of the other two numbers squared. So that is 60 squared plus 11 squared. And if you see, 61 squared is this over here, 3721, and 11 squared, which is 121 plus 60 squared, 3600. If you add this both, you do get 3721. So, in fact, 11, 60, and 61 are a Pythagorean triplet. So, it tells us to check that all these are Pythagorean triplets as well. We are not going to do that for all of those, but like 3, 4, and 5 are very easy. You can just check this. So, 3 squared would be 9, plus 4 squared would be 16, and 9 plus 16, let me just write that better. So, 9 plus 16 would be equal to 25. And as you can see, 5 squared, which is the biggest number, so 5 squared is also equals to 25. So that means this is a Pythagorean triplet. You can, as a practice, try to verify all of the other ones on your own. So again, for more information, this is just saying that what a Pythagorean triplet is, and there are some more formulas on that. So this formula can be used to get a lot of different Pythagorean triplets. So this is what was explaining what Pythagorean triplet are. And this is a formula that can be used to generate Pythagorean triplets, but not too valuable for exam. So let's go ahead. So now we have two properties related to different types of right angled triangles. So there is a property about a right angled triangle whose angles are 30, 60 and 90. Then there is a property whose angles, for triangles whose angles are 45, 45 and 90. So if you have a triangle which is a right angled triangle which has a 90-degree angle in it, if you have such a triangle and the other two angles are 30 and 60 degrees, then we can say that the side that is the opposite to the 30-degree angle. So this is the 38-degree angle right here. So the side which is opposite to this, that means this side over here, the MN is going to be half times the hypotenuse. So LN, half times LN. And the side which is the opposite to 60-degree angle. So this is the 60-degree angle over here, and this is the side opposite to that. So this side over here, which is LM, this is going to be root 3 times 2 into ln. And why is that so? So this is just basic trigonometry, since we have sine theta equals to opposite upon hypotenuse. and we have that sine 30 equals 1 half. So since sine 30 is opposite upon hypotenuse, we can say that opposite equals to hypotenuse, opposite upon hypotenuse equals to a 1 half. And this hypotenuse we can take to that side of the equation. So we can multiply both sides of the equations with the hypotenuse to cancel it from here. So we'll finally get opposite side, which is the side opposite to this 30-degree angle, will equal to 1 half times the hypotenuse. So all of these properties are nothing but just derivations from simple trigonometry. Now the next is the property of the 45, 45, 90 triangle. So again, this is related to the sine 45, which is 1 by root 2. But you don't have to remember that. You can also just directly remember this property, and that is the sides which are opposite to these 45-degree triangles, both of them. So this and this are nothing but just 1 by root 2 into the length of the hypotenuse, which in this case is said y. So this over here is the property. So you can remember this, both these properties. These might be helpful while solving numericals. Now this is activity, that is that if we have two right angle triangles, we can join them from tip to tip like this, and that creates a 90-degree angle over here as well. And then we can join this line to make a trapezium, and then you can just prove the the Pythagoras theorem using the areas of this trapezium and these individual triangles. So we are also not going to get too deep into that, but this is a fun activity if you want to try it out. So now what we are going to do is we are going to prove a simple theorem. So now this is the first theorem from this chapter, and this theorem talks about right angle triangles, and it says that when we make an altitude from the hypotenuse, so that is a perpendicular 90-degree line from the hypotenuse that touches this point B. So if we make such a line, then the true triangles that will be formed, this triangle over here and this second triangle over here, both of these triangles are going to be similar to each other, and they are also going to be similar to the original bigger triangle as well. So if I write all these triangles separately, so if you see this gray area over here, so this is a triangle that was formed, and there is this triangle over here, so I'll make it with this color. So you can see that this is another triangle that is there, and in the green I'll make the original triangle. So this is the original triangle that we have. So the theorem says nothing but just that all these three triangles are similar to each other. So this small triangle is similar to this original triangle. This other small triangle is also similar to this original triangle, and these two smaller triangles that were formed are also similar to each other. So let's see how do you go about proving this theorem. So let me just clean the clutter a little bit. So first of all, we just draw this. This is the only construction in this proof. We have to draw this altitude. And what we have to prove is all of these triangles that have been formed are similar to each other. And how do you do that? The proof is super duper simple. Because in the last chapter, if you remember the similarity chapter, we learned about something called AA test. Now, what is the AA test? AA test is nothing but the angle-angle test. And the angle-angle test says that if there are two triangles, so let's say there are two triangles, and if inside those two triangles there are two angles that are equal to each other. So let's say in these two triangles, this angle is equal to this angle and this angle to this is equal to this angle, then both of those triangles are similar to each other. So what we can do is, first of all, we take the ABD, so this upper small triangle that was formed, and compare it with the original ABC triangle. So in that, we have this angle over here. If you see, this is a common angle. This angle is there in both of these triangles. So we have one common angle right here. And if you see that our original triangle had a 90-degree angle over here because we started with a right angle triangle. And this new triangle also has a 90-degree angle right over here because we have created an altitude. And altitudes are supposed to be perpendicular. So we have a 90-degree angle over here as well. So both of these triangles have a 90-degree angle. So therefore, we have two angles which are common in two triangles, and then we can say using the AA test that these two triangles are similar to each other. And you can do the same thing in this other small triangle as well. So let's just quickly do that. So let's say now we are comparing this small triangle. So in this angle over here, the angle C, this angle is present in this larger triangle as well and in this smaller triangle as well, right? So this is one common angle that we got, and this triangle also has a 90-degree angle over here, and our original triangle, the big one, has a 90-degree angle over here. So both of these triangles have a 90-degree angle. So again, since we got two angles that are common between the two triangles, we can use the double A test and say that these two triangles are similar to each other. And in the last chapter, we also learned about a property called transitivity, where if there is, let's say there is a triangle A, which is similar to this triangle C, which is similar to a triangle C, and then we have another triangle B, which is also similar to this triangle C, then A and B both are also similar to each other. That is just the property. It is very, very similar to saying that if A is equal to B and B is equal to C, then A is also equal to C. So this is something that we learn about addition and all. So this does not apply to everything, obviously, but over here it does. So that is why we can use this property and say that the two small triangles over here, this one and this blue one, these two triangles are also similar to each other because they both of these ones are similar to the original bigger triangle. So again, if you try to understand the steps that we are taking to prove that how these triangles are similar, you can easily do that in the exam as well, and you will just have to practice the notation. So always practice the notation because that is very much important in the exam. But the overall flow that we go through to try to prove this, that these two triangles are similar to each other and with the original one, is just that you use the double angle test both the times separately. We compare each of the smaller one with the bigger one separately, and then for both of these comparisons we just use the double A test. And then at last we just say that since both of them are similar to the original triangle, both of them are also similar to each other. So let's go ahead. So now this is also a very small theorem again right over here. So this is just a theorem of the geometric mean, and that means this theorem, what the theorem says is when we draw an altitude very similar to what we drew in this proof in a right angled triangle, the ratio in which these things are cut over here is the geometric mean. So this point S over here is the geometric mean of P and R. So now what is a geometric mean? So let's just quickly see that. So you are familiar with a algebraic mean, right? So if we have two values, let us say A and B, so the algebraic mean for that would be just A plus P divided by 2, right? So the geometric mean is nothing but we find the geometric mean using the product. So the geometric mean for the same two values A and B would be A into B and the square root of that. So that is what the geometric mean is. So what this theorem says is that this S point where we draw the altitude such that it is perpendicular to PR and touches the point Q is going to be the geometric mean. So how do you prove this? So first of all, the QSR, the smaller triangle, this upper smaller triangle over here is similar to PSR. So the smaller triangle over here. So this is this one and this green one is the upper one. They both are similar triangles and we just proved that 5 minutes ago. So you can watch a recap of that if you have forgotten how to do that. But because of that, we can say that QS, which is this angle, which is this side over here, the altitude side, QS upon PS, this side over here, is equal to SR upon SQ. So what is SR? SR is this side over here and this upon SQ. So now you're thinking, why are we taking, let me take some different colors to make it easy. So from the first triangle, we took this side and compared it with this side from the second triangle. And then again from the first triangle, we took this side and compared it with the second triangle over here. Why? Because if you think about it, this triangle has the 90-degree angle over here, right? And this triangle has the 90-degree angle over here. So to get from this triangle to get to this triangle, you will need to try to flip this on itself over here. If you think about it, if you think about this line over here as a crease on a paper, then if you flip this thing over here, then you get the corresponding sides. So that means that this side over here corresponds to this side over here, and this side corresponds to this side of this triangle, and this side corresponds to this side. So because of that, we can say that QS, which is this side, and if we compare it with this side over here, then we can say again that QS, again this side, and we can also compare it with this side because in both the triangles we are comparing crisscross. If these triangles were like this and the other one was like this, then what are we comparing actually is we are comparing this with this, and we are comparing this with this. We are comparing this with this, and we are comparing this one with this one. We are comparing it in a cross way, but that doesn't matter because they grow with the same proportion, because that is what the similar triangles are. So you can take these comparisons, and again you can take the other comparisons as well. So again QS upon PS, which is QS upon PS, is also equal to SR, which is this SR upon QS. So we are taking the same thing twice, and then what we do is, because you can also, if these were the triangles, let me draw them again. So since we compared this and this and this and this, we could have also compared this and this and this, and we have still gotten the same results, because you can just so you can compare any of these to just what we actually just want to get is the QS upon PS and the SR upon SQ. So we want to get the QS twice, and we want to get this side and this side. So that is our main goal. That is what we want to get. So because then what we can do is we can take this PS over here and take this QS over here, and we'll get the QS squared equals to PS into SR. So that means that QS is the geometric mean of PS and SR. So why? Because this is by definition what the geometric mean is, because if we take a square root over here, then we will just get a QS. So just like we saw in the previous example, the square root of A into B is the geometric mean of A and B. So that means the square root of PS and SR is the geometric mean of PS and SR, which is QS. So again, just a little bit of correction. The geometric mean is the whole segment. This whole segment is the geometric mean of these two segments that have been formed because of this division, and not the single point S. So that's a bit of a correction over here. But apart from that, this also is just very easy to remember. This proof is also not very difficult. Let's move ahead. So now finally we have reached the Pythagoras theorem, and over here we are trying to prove the Pythagoras theorem. So how do we do that is also very simple. Just follow along with me and you'll understand this proof in no time. So again, what is given is that we have a triangle, and one of this angle over here is 90 degree, because we are given a right angle triangle, right? This is just given. And what do we have to prove is that AC squared, so this hypotenuse over here, AC squared. So square of this hypotenuse is the square of this plus the square of this, and it is the root over the square of this and the square of this, the length of the hypotenuse. So how do you prove that? You again start by drawing an altitude. So we draw a line perpendicular to the hypotenuse AC such that it meets point B. So we draw this particular perpendicular line segment on AC. And now in this right angle triangle, we just saw in the first proof in this chapter that all of these angles are similar to each other. So what we will do is, again, we will take the similarity of the bigger triangle, the original triangle, and the upper triangle first. So we are first considering these two triangles, and we are going to use the corresponding side ratios. So this is what perpendicular triangles mean, right? The corresponding sides grow in the same ratio, so they have the same ratio. So what do we want is, you can write this point as well, that all of these are corresponding sides, but you can also just directly write this point in the exam and just don't forget to mention that this is corresponding side, because if you don't mention this, you might lose some marks over here. But you actually don't even have to write all the corresponding sides. You can just write the main corresponding sides that are needed for this proof. Just mention that they are corresponding sides, or you can also do it this complete way, your choice. But what corresponding sides we are going to take, that is the main point. So what is we are going to take is, we will take AB, so this side over here, AB upon AD. So AB we are taking from the bigger triangle, and from the upper smaller triangle we are taking AD, because that is the corresponding side, right? Because if this is the right angle over here in this upper triangle, then this is the longer side apart from the hypotenuse, right? This is the upright side over here, and if this smaller triangle, if you drew it over here, if you just flipped it a little bit, it would look something like this, right? So this is the side corresponding to this side in the bigger triangle. You can just see that. So that is why we will take AB and AD, and that will be equal to the hypotenuse of the both of the triangles, the ratio of the hypotenuses. So bigger triangle, the hypotenuse is just AC, the AC over here, and in the smaller triangle, the hypotenuse is this one, AB. This AB is the hypotenuse for this smaller triangle, as this is opposite to the 90-degree angle, right? So we will take this ratio, and in the other triangle, so in the other pair that we are comparing, that is the whole triangle plus the other smaller triangle, this triangle that is below. In this also, what we are going to do is, we are going to take this BC and this smaller side, and we are going to compare that with the hypotenuse. So the hypotenuse for the bigger one is just the AC, and for the smaller one it is BC. So when we write those ratios down, what we get is just AB upon AD equals to AC upon AB. And from this one over here, what we got is just BC upon DC equals to AC upon BC. Now what we do, we just cross multiply. So in this we have AB both the sides over here in this equation, right? So these two will get, so we get AB squared if we take this up and we take this over here, which is equal to AC into AD. And over here what we get is BC squared equals to AC into DC, right? So now what we do is, we just add both of these equations together. So let me just make some space over here. So when you add both of these equations together, what you get is AB squared plus BC squared. So that is this squared plus this squared is equal to, you get AD, you have AC common in both of them, right? So you can take AC outside. So AC into, let me just rewrite this, AC into AD plus DC. And what is AD plus DC? So AD plus DC is nothing but AC again. So this part inside the bracket is also AC. So that is just AC into AC. So you get AC squared. And that is exactly what we were trying to prove, that AC squared is equal to AB squared. So AB squared and BC squared is equal to AC squared. This is what we are trying to prove. So again, you'll have to practice the notation to be able to write this proof very quickly in the exam. But here is the general flow of trying to prove this theorem. So what you do is you just draw a perpendicular over here, and then we compare the bigger triangle with this upper smaller triangle and the lower smaller triangle separately to get the ratios. And what ratios we take is the hypotenuse of both the triangles and the longer sides apart from the hypotenuse, and then we can just cross multiply and add those equations to get the Pythagorean theorem, the Pythagoras theorem. Now the converse of the Pythagoras theorem is nothing but the opposite statement. So that is, if there are two triangles where the length of one side squared is just the summation of the other two sides squared, then that triangle is a 90 then the triangle is a right angled triangle. That is, that triangle has a 90-degree angle. So I'm not going to go into the proof of this for now, because this is just a SSS test type of a proof, not very intuitive. We just directly use the Pythagoras theorem over here, and then we say that this one is equal to this one, and therefore they both have to be similar. And because they are similar, if this has a right angle over here, this also has a right angle over here. So these are all the points that they have given us. So you can easily remember all those. You can just go through these. So this is just the similarity of the right angle triangle. Then this is what the Pythagoras theorem is, and this is what the converse of the Pythagoras theorem is. And we also just learned that 60, 30, 90-degree properties as well, that if there is a right angle triangle and there is a 30-degree angle over here and a 60-degree angle over here, then the side opposite to the 60-degree one will be the root 3 by 2 times the hypotenuse, and the side opposite to the 30-degree one will be the half times the hypotenuse. So this thing you can derive from trigonometry, but if you remember this, you will be able to solve questions faster in exam. So some solved examples. So now we look at an interesting application of a Pythagoras theorem. So we will use the Pythagoras theorem to derive a interesting result. And that is, so the Pythagoras theorem is saying that for a 90-degree triangle, we will have this side, let's say this is A, and let us say this is B and this is C. So we have C squared equals to A squared plus B squared. So this is true for a 90-degree triangle. But what if we have a simple triangle, not a 90-degree triangle? So we will use the Pythagoras theorem and derive that for a normal triangle that is not a 90-degree triangle, we have one of the sides that is AC over here. So AB. So AB squared will be equal to the other side, that is the BC, the bottom base, you could say BC squared, plus the other side, which is the AC squared. So this would have been true. So if we would have stopped over here if this was a 90-degree triangle, but since this is not, so we will subtract the base 2 times the C into the DC. And what is DC? So DC is just the height of this triangle. So let us try to prove this. Let us just see how this is proved very quickly. So first of all, in this figure, let us just call this C, let us call this B, and let us call this whole thing A. So this small part over here would become X, and then this part would just become A minus X. So after giving all these names, using the Pythagoras theorem in the triangle ADB, so this bigger triangle to the right over here, this triangle over here, if we use Pythagoras theorem on this, then we get just that C squared is just A minus X whole square plus P squared. because this p is the other side. So that means that a squared equals c square equals to a square minus 2x plus x square plus again p squared, and in the triangle ADC, so this ADC, the other one over here, b square is just the p square plus x square. So p square equals b square minus x squared. Right, this is just basic algebra, nothing fancy over here. And then we just substitute the value of p square. So this is the value of p square that we got in the second equation, right? That p square is b square minus x square. So we will take this value and we will put this value over here into this equation. So we will substitute the value of p square from the equation 2 into the equation 1. So instead of p square over here, we will write b square minus x square. So that is exactly what we do. So that means c square is equal to a square plus b square. So this plus b square minus 2ax, and this x plus x square and minus x square, they just cancel each other out. So this is the final result that we get. And then what we do is we just substitute the names of the line segments back into this. So c squared is just, we were calling the length of the ABC, so we just write that back, AB. A squared was nothing but BC, B squared nothing but AC, and over here 2 times AX. So 2 times A was BC, so 2 times BC into X. What was X? X was nothing but DC, so DC. So what we did was we just substituted these values back, nothing very complex. So this is how we can just simply get this interesting result for a triangle that is not a right angled triangle. So this is just the same example, the same result, but this is using the other triangle in which it was skewed a little bit to this side, but we still get the same result, in which so in this, the altitude was getting created inside of the triangle. In this, if there is a triangle where the altitude gets created outside, you can still get to the same result. So you can go through this one as well, but we finally overall get to the same result. So now coming to this is the last theorem of this chapter, the Apollonius theorem. So what this theorem says is that if there is a triangle that is ABC, this ABC triangle, and if M is the midpoint of the B and C, so this side, the M is the midpoint for this side, so that means this side over here and this side over here. If we divide it over here, then this side, both of them are equal. So if M is the midpoint, so what it says is that then AB squared, so that is AB squared, so this side over here, AB squared plus AC squared, the other side, this side, is equal to 2 times AM squared, which is this point to the middle, so the line from A to the middle point of BC, plus 2 times BM squared, so this line over here. So this is AM squared over here. So this is again a very interesting result that has been derived using the Pythagoras theorem. So but this has a special name called the Apollonius theorem because this. So let's see how we can prove that. So this is the statement that we have to prove. We just saw this statement right now on this triangle, and given is that we are given a triangle ABC and M is the midpoint of the side BC. So this triangle itself is given and M is the midpoint, that also is already given. So we don't have to prove that M is the midpoint. We already know that M is the midpoint. So this is the proof. So the proof itself is not at all very long. So for this proof, what you have to remember is that we just use this result that we just got in the earlier section. So what we do is, what we say that if AM is not perpendicular to BC, so this is the case when we consider that AM is not perpendicular to BC. So there is another line AD which is perpendicular to BC and D is not the midpoint. there is also a case where M can also be perpendicular to BC. So AM can be perpendicular to BC, and in that case, the triangle would look something like this. So this line itself will be perpendicular, and this point M itself would be the midpoint. But in this case, M is the midpoint, but that is not perpendicular, and the perpendicular point is this D point over here. So this is the scenario that we are considering. And in that particular scenario, if that is the case, then what will happen is that one side of this M will be an obtuse angle greater than 90 degree, and the other side will be an acute angle less than 90 degree. So an obtuse angle greater than 90 degree. Because if this would have been perpendicular, then both the sides would have had an right angle. But because this is not, then one side is obtuse and the other side is acute. So let's go ahead. So in this figure, AMB, so let us say that AMB is the obtuse angle and AMC is the acute angle. So again, it does not matter if this side has the obtuse angle and this side has the acute angle, because everything is symmetric. But in our particular case, it happens to be that AMB is the obtuse angle. So what we do is, from the above examples, from these results that we got over here, we can say that AB squared, which is this AB squared, is equal to AM squared plus MB squared, the other side, minus 2 times MB into MD. So this is again the same thing that we just proved earlier, that this side squared over here would be the other two sides, the sum of the squares of the other two sides, minus this bottom side twice, and the length to the perpendicular. So this length over here, this BC, in the case that the perpendicular was outside the triangle, which is the case over here, the length can be DC. This length can be outside the triangle as well. It does not matter. So this is the first equation that we got. So we did not do anything. We have just taken this equation directly from this particular result that we proved just some time ago. So you just have to remember this result, and then you have to write it down for this side of the triangle over here. And once you do that, what we do is we just write this for this side of the triangle over here again. So for this, what we write is AC squared is equal to AM squared. So again, AM squared plus MC squared minus MC squared into MD. So again, this is the very same result, but for this triangle. And because we know that BM is equal to MC, so MB is equal to MC, because it is given that M is the midpoint. This is already given to us. So since MB and MC are same, what we do is we substitute that in the second equation. So in the second equation, instead of MC, we will write MB. And now what we will do is we will consider this the second equation and this the first equation, and we will going to add these two equations together. So we will add them, and what we will get is AB squared plus AC squared is equal to 2 times AM plus 2 times MB, because MC we substituted as MB. So this is again the result that we just wanted. And now it says that you can write the proof yourself if it was perpendicular, and in that case we could have just used the Pythagoras theorem on both the sides, because let us say that it was perpendicular, then you could have written that this side, let's call this A squared and let's call this B squared. So you could have written A squared equals to, so this is the side over here, this is the AM, so let's call this Z. So Z squared plus this smaller side over here, which is MB in our case, so let's call this Y squared, and B squared would also have been z squared plus, let's say this is p, this side over here, this thing over here must be p, but since p is also equal to over here y, because again this is still the midpoint, right? It does not matter if it is perpendicular or not, it has to be the midpoint, because then only we have the Apollonius theorem. So we can again write y squared over here, and we would just get a squared plus b squared would be equal to 2 times z square plus 2 times y squared, which is just the result that we got over here. So if for the general case we use this result that we derived, to prove the Apollonius theorem, and if AM is happens to be perpendicular to BC, then we use the Pythagoras theorem to derive the same result. Again, you are going to need practice. So practice this once or twice before your exams. But since now you know the flow to try to prove this theorem, you will be able to easily solve this in your exam. So again, now we have some solved examples. We are not going to go through that. And this was the last theorem of this chapter. And now we move on to the circles chapter. So if you are also preparing for your 10th board exams, don't forget to subscribe so you do not miss out on anything, and see you in the next one.